Okay, I think we can get started now. Hi guys, so today we're gonna start something new, a new chapter, and hopefully we'll spend only 2 lectures on this. But I would say we'll spend at least 2 weeks. I think. Okay. All right. So we'll spend at least 2 weeks. Can you guys hear me well? Okay. We'll spend at least 2 weeks. And wait, let me share content. And I don't know if I'm forced to do any other lecture, but I hope that's not going to be the case.
You're muted, sir.
Now, can you hear me? Well?
Yes.
Okay, that's good. Sorry about that. I think somebody's mic is on. I think Aaron. I can. Okay. All right. So today we're going to start with something new. We will talk about vector spaces. And well, just like I said, I hope we will only 2 lectures will be enough for this, although I'm not sure, but we'll see about that. But before I go into this, I want to ask you a question. I recorded a video yesterday about I did another review session on my own. I didn't want to tell you to be online and everything. Did you get that? Did you get the video that I sent you? Okay, that's good.
Yes.
So you're able to follow it and everything, right? Okay, that's good. All right, so we're going to start with the vector spaces today. And it will be quite a long chapter. If you look at my notes, there are 52 pages of notes that I uploaded on my website. And before I even go and talk about vector spaces and what they and their properties and so on, I want to talk about something. For example, what it means for a vector. What do we mean by vectors in Rn, for example? I think somebody's mic is on, and I don't know. I think Jet. I think your mic is on. And VJ. Anyway, okay. So now let's talk about vectors in Rn. So vectors vectors in Rn, and I assume you are already used with this. Probably you have seen them in engineering and stuff. So when you have a vector in Rn, and let's take n equals 2. So we want vectors in the plane. So vectors in the plane are something like this. So let me draw a picture. And let's suppose that this vector will start from the origin. So it starts from here and it goes all the way like this, right? Let's say this is my vector x. And this is at this point, let's say, is I have this coordinates x1, x2. So this will be what we will call, oops, sorry about that, a terminal point. Okay, so this is the x-axis and the y-axis. So this is the vector. So that is, we can write this vector x as using its coordinates x1 and x2. So we say that these coordinates x1 and x2, so the coordinates x1 and x2 are the components of the vector x. Okay. Well, this is just one vector considered in the plane, so I can consider many other vectors. For example, I can consider, let's say, vectors. For example, let's consider u with coordinates u1 and u2, and let's say v with v1, v2. Sometimes you put an arrow here if you want, so that you can to symbolize the fact that this is a vector. But when you write this like a component, when you write the vector's components, it's quite clear it's a vector. But anyway, so we say that two vectors, u and v are equal. Neil, I think you should turn off your mic. So two vectors u and v are equal if and only if its components are equal. For example, you have u1 equals v1 and u2 equals v2. Right? So this is what happens when the two vectors are equal. And now let me give you an example, and the example I have in mind. So let me give you an easy example. And let's suppose I want to represent the vector, let's say u of components or coordinates, whatever you want to call it, 2, 3. So this is nothing else than just the segment coming from the origin. And this will be so you'll have something like this. So let's, here is the vector. And here is the terminal point. Let's say u of components 2 and 3. Right? So that's the vector 2, 3, right? So it's the segment from the origin to the point of coordinates 2 and 3, as you can see it now, right? Let's say here I have the unit is 3 and here it's 2, although it doesn't like quite look okay, but anyway, imagine this. And now let's say I want to represent another vector. So this is another b. Let me give you a vector v of coordinates, let's say -1 and 2. In this case, so I'll draw the same picture. So you have x and y. And this time I want to represent this vector of -1, which is here, of coordinates -1 and 2, which will be here. So this vector will be something like this, right? So this is my vector v. And this here will be the terminal point of coordinates -1 and 2. So this is how you represent vectors. So here it comes from the origin. So let's keep that in mind, right? So this is how we represent vectors. Now, of course, we have seen what it means for two vectors to be equal. Now we want to see what kind of operation. So the question we want to ask is, what kind of operations do vectors in plane satisfy? The plane satisfy. So we want to see that. Well, the short answer is that all the operations that you can imagine, they are satisfied. Although I wouldn't go that far with multiplication of two vectors, basically the dot product. That will be a little bit more not complicated, but we need to be a little bit more careful with that before we define it. But the first basic operation will be, for example, vector addition. This is the most basic operation, vector addition. We're interested in this operation first and foremost, because from this operation we can derive the others and so on, but we're interested in this. Okay, so with vector addition, the story is like this. So suppose I have two vectors. So let's say I have u a vector and v a vector. So these are two vectors. And let's suppose that u is of coordinates u1 and u2, and v is of coordinates v1 and v2. Okay, so these are the vectors. As you can imagine by the definition, the addition u plus v, so here by the definition, I'll write it here, definition, is nothing else by just adding their components. u1 plus u2, and the second component will be v1 plus v2. That's the vector addition. That's how you define it. Right? So it's very simple. And we can represent this geometrically. So geometrically, this means that the two vectors, let me just draw the picture. So x and y, let's say, and I have two vectors here. Let's say I have u is here. I have this vector u and of components u1, u2, and now I have this vector, let's say here, v vector of components v1 and v2. Okay, now guess what? The addition of these two vectors will be geometrical, represent just like the parallelogram law. So you draw the parallel line to the vector v, and you draw the parallel line to the vector u. When they intersect, guess what? The resulting vector will be the sum. So this is my vector u plus v. U plus v. And of course, the components will be u1 plus u2 and v1 plus v2. So this is what we call the parallelogram law. So this is just nothing else. This is what I drew here is nothing else than just a parallelogram having u and v its adjacent sides. So this is what we call the parallelogram law. Rule or law, whatever. So this is how you add two vectors geometrically. You have the two vectors and the resulting vector, which will be basically the diagonal of the parallelogram. So you draw, when you have the two vectors and they connect to, they have a, I don't know, here they meet in the origin, right? So you just draw the parallel lines to each vector, and then you intersect them, and the resulting vector will be that the diagonal. All right, let me give you a quick example of how you add two vectors. So this is a quick example of adding two vectors. For example, let's say I have u of components 1, 4, and v of components 2 and -2. As you can imagine, based on what we said so far, u vector plus v vector is nothing else than just 1 plus 2. The first component, the second one is 4 plus -2. Exactly, so it's 3, 2, correct. Just like Nail says, it's 3, 2. So the addition is very simple. Probably there is no need for me to do any other examples. It's quite simple the way. Okay, now there's one other thing, and you can you might expect this from operations with matrices. Well, we talked about vector addition, right? This thing here. But another operation, let's put this one. Let's put the second one. Will be scalar multiplication.
I forgot I had class right now. It's for, yeah, it's for extra credit though. Because if I attend the lectures,
Wait.
I get 10% extra credits. I'm like, yeah, let me take that.
Yeah, we know that. We can hear you actually, Matt. Yeah, it's extra 10%. Also, I forgot to say one thing. Those of you who cannot, I don't want to be unfair to those other people who cannot attend this. And for those other people who cannot attend this live lectures, I'll offer them the opportunity to get those 5% extra percent if they attend the last review session before the final. Hopefully there's going to be only one. So if they attend that, they'll get only those who cannot attend these lectures will get those 5%, so that they have an opportunity as well to get some extra credit. All right. So the second operation is the scalar multiplication. And we have talked about this when we multiply, for example, in the case of matrices, when we multiply a matrix by a scalar, well, why not do it for a vector as well? So to multiply a vector v, so I'm going to put an arrow on v, but usually in my notes is not, but you can do it. If you like the arrow, you can put it. If you don't like the arrow, it's fine. You don't have to do it. So to multiply a vector v by a scalar c, multiply. So we multiply each of the components of v by c. So in other words, we have the following. We have c, this is a scalar, times v. That's why I want to put the arrow here so that you can see the difference between the two. But anyway, let me specify it. Scalar vector. And suppose this vector will have components v1, v2. So it's c times v1, v2. And guess what? You'll multiply c by each component. So it will be c v1, c v2. Okay, that's how we're going to do it. So this is a scalar multiplication. It's another operation. And for example, this will allow you, the scalar multiplication will allow you to define the opposite of vector v. So if we have something like the opposite vector of v, let's say, this is nothing else than just negative v. We're going to write it like this. So this is the opposite vector. So this is the opposite vector of v. Okay, and guess what? This will be based on what we have said previously. This is nothing else than just, so the negative v is nothing else just multiplying the scalar -1 times v. So again, this is a scalar, and this is the vector. And that's it. This is how we define the opposite vector of v, is basically negative v. Also, based on this, we can also we can define the subtraction of two vectors. So we can subtract two vectors. So the third operation, subtraction. So we can define u minus v vector. In fact, let me write it with u vector minus v vector. Guess what? This is nothing else than just u plus negative v, the opposite vector. And if we want to write this component-wise, so let's assume that u is u1, u2, v is v1, v2. So this will be nothing else than just, let's write it, u1, u2 plus negative v1, negative v2, right? That's the opposite vector, negative v. So this will give us is u1 minus u2, v1 minus v2. So it will give us this vector, which is u minus v, and its components will be u1 minus u2 and v1 minus v2. Okay, so that's the subtraction. So the vector v is subtracted from u by adding negative of v. Now let's see some operations where we let's see an example where we apply all these operations. These are very basic stuff what I'm doing now. Oh my God. Can you see the?
No.
Okay, just give me 1 second. Oh my. It's interrupted for some reason. Okay. Okay, you can see it now, right?
Yeah.
All right, great. Okay, so now let me give you a quick example, a very basic example. So suppose, and I'm going to take example 3 from the notes. Let's take these vectors. So consider the vectors, let's say v. Okay, let me write them like this. U is 3, 4, and v is -2 and 5. Okay, so we have these two vectors, and we're interested in compute the following. Let's say I want to just directly, I don't want to do it step by step like it is in the notes. U 1/2 times v plus u. So you see, well, it's easy, and probably these operations has the following meaning. So I'm multiplying the vector v by the scalar 1/2, and then I'm adding this to the vector u. So you can do it separately if you want. There is no problem for you to do this. So let's see, 1/2 times v vector. So this is the scalar 1/2. So it's 1/2 times the vector v, which has components -2 and 5. And now, well, Neil wants to, yeah, probably to, okay. It will be, okay, let's do it slowly. So it will be 1/2 times -2, which has been -1. And wait, you have, wait, Neil, what did you get there? 265. You see, how did you have 265 when the vector will only have 2 components? How did you get 3 components?
No, it's 6.5.
Say that again.
Because 5. I said 6.5 because 5 divided by 2, 2.5. Then you plus. Oh wait, yeah, 2.5.
Ah, okay. Sorry.
4.
Yeah. Okay. I see now. It's not the comma between, then it's 2, 6.5. Okay. You see, you should leave them as fractions sometimes, because you might get. All right. So, and this will be 5/2, right? And now you can add. So u plus 1/2 v will be nothing else than just 3, 4 plus, and now you have this vector -1, 5/2, and now you just use the addition of vectors that we have seen previously. So this will be, you see, you have the negative there, so it'd be 2, and this will be 16. Oh wait, 13/2. Just like Neil says, 6.5. Yeah, that's the vector. All right. So that's the example. Probably I don't need to do any more examples of this type since it's quite clear for everybody what's going on. But now I want to do something, and this will be very important. So the question is, what properties do vector operations satisfy? That is the question we want to answer. You've seen the fact that we've done the same thing for matrices, right? We want to see how they behave when you add them, when you multiply matrices, when you multiply by a scalar, when you blend everything together. We have two operations like distributivity and so on. You've seen how they act. So the same thing will happen here. So the answer is given by the following theorem, and it's a quite long theorem, but I'm gonna write it once. So the properties, this theorem will concern the properties of vector addition and scalar multiplication in the plane. But of course, as you can imagine, this can be generalized also for vectors in R3 and so on. Okay, so let's consider let U, V, and W be vectors in the plane. And let C and D be scalars. Okay, I'm going to put an arrow here so that you know that they're vectors, and C and D be scalars. So these are scalars. Then part A, U plus V, so when you add these two vectors, is a vector in the plane. And it's nothing else. We have seen how we add them. It's nothing else than just U plus V vector. That's what it is. So it's a vector in the plane. So in other words, this means that we have what we call closure under addition. This is very important because this operation, it's a must for further properties to hold true. Okay, so we have the closure under addition. Then B, U plus V vector. So when you add them, the addition is commutative. So it doesn't matter which way you add them. It's the same as V vector plus U vector. So we have commutativity. So the addition is commutative. C, if we have something like associativity, so we have U plus V vector plus W vector is the same as U plus V plus W. So it doesn't matter the order. So this is what we call associativity. Okay. Now, we can also add by the null element, so by the null vector. So U plus, let's say, 0 vector will be just the U vector. So this is the, let's say, the identity or the null element. Okay, I'm going to call it the identity vector under addition. This is very important because we'll have also an identity vector under multiplication, under addition. Okay. E, what else can we do? We can add by the opposite. So U plus negative U vector. It will be, guess what? The 0 vector. And so if I'm adding two vectors by the first property, pay attention. It will be a vector. It's not going to be a scalar. So when I'm adding two vectors, I obtain a vector. So when I'm adding U vector with the opposite of U, it will give you the 0, but the 0 vector. So this will be what we'll call, let's say, the inverse vector under addition. Okay, the inverse vector. Okay. Now, since we've exhausted probably all the operations with between two vectors here with the addition and stuff, let's go further. Maybe some scalar multiplication. So if I multiply, let's say, the scalar c by the vector u, let's say, this is a vector in a plane. So we have what we call closure under, so this is very important word, closure under scalar multiplication. Right? So once again, when you multiply a scalar by a vector, you'll always gonna get a vector. So keep that in mind. Okay. Now let's see some other properties. What happens when we multiply? Let's say we have a scalar c, and we add two vectors, and we multiply them by a scalar c. So we have this so-called distributivity. So this is nothing else than just multiplying the scalar c by the vector u, and then you add them by c times vector v. So this is what we call distributivity. Or we also have another type of distributivity, c plus d times u vector. So I'm adding this time two scalars. So this would be c times u vector plus d times u vector. So this is again distributivity. Right? And now let's see two more. So let's say maybe we want to do something like distributivity in this way. So instead of addition, instead of adding two scalars, maybe I should multiply them. So this is nothing else. So there's just multiplying the two scalars, and then you multiply by the vector u. So it's called, let's say, associativity of multiplication. And finally, the last one, k. Oh my goodness. If I'm multiplying the scalar 1 time by the vector u, it will be nothing else than just the vector u. So this is what we call, we have seen the identity vector. So this is what we call the identity, well, multiplicative identity. Let me call it like this. Wow. So there are a bunch of operations. I want you to look at them. Let's look at them a bit. So there are a bunch of operations satisfied by vectors in the plane. Right? You see them? You can add them. It doesn't matter which way you add them. It's because the addition of two vectors is commutative. Then you have associativity. Then you have the identity vector under addition, so the null vector, and you have the opposite vector, and so on. You can multiply by scalars. So you're pretty much, you can do whatever you want to do with vectors. It's actually even more, well, for matrices, remember, it try to make a parallel, to draw a parallel between the operations with matrices and operations with vectors, and you will see kind of they're the same. Okay, so these are the operations, and now, so these are the vectors in R2. Guess what happens? So the question is, what happens in higher dimensions? In higher dimensions. And when I say, of course, I mean, I want to keep it real. And when I say higher dimension, I mean Rn. What do you think? Do you think all the properties will hold true even in higher dimension? What do you think? somebody answered, but I want to see somebody else too. What do you think? So Liliana says yes. Do you guys agree? Looks like, yeah, okay. So most people agree with this. Well, the short answer is probably, as you can imagine, is yes. So what happens in higher dimensions? So perhaps everything will stay the same, right? So pretty much the same as in R2, as in as in the plane. Well, I'm not gonna do the same thing. You can imagine. I'm just gonna say what it means for vectors. Let's say vectors in Rn. Vectors in Rn. So as you can imagine, the discussion from vectors in the plane can be extended to vectors in on Rn. So let's see what a vector in Rn means. So an ordered n tuple represents a vector in the n-dimensional space. For example, an ordered triple, let's say, has the form x1, x2, and x3, right? So these are the three components. So this is a vector in R3. Now, the set of all n tuples is n space, is an n space, and is denoted by Rn. So let me say it explicitly. R1 is the one space, which is the set of all real numbers. Real numbers. The R, remember, the set of real numbers that you have been so used to. R2 is a two space, which is the set of all ordered pairs of real numbers, right? This is R2, or basically are the vectors in the plane. That's what we mean by R2. And then we keep going all the way to Rn. So we have the n copies of R. So it's the n space is a set of all ordered n tuples of real numbers. So that's and now I want to see what is an n tuple x1 xn. So an tuple, let's say x1 x2 xn, can be viewed as a point in Rn, with the xi's as its coordinates. coordinates. Or as a vector, let's say x, x1 with components x1, x2, xn. With xi's as its components. All right, so now let me formally define the vector addition and scalar multiplication. So definition for vectors in Rn. That's what I want to define. So let U with having these components, U1, Un, and V, having V1, V2, Vn, be vectors in Rn. So I'm considering this time two vectors in Rn. And let C be a real number. So this is what we call basically the scalar, real number. Let me say it here is a scalar. Okay. Now we define the sum of U and V. The sum of the two vectors will be nothing else than just U vector plus V vector will be U1 plus V1, U2 plus V2, Un plus Vn. So we just add the components. That's what we do. We add two vectors, we add their components. So that's the sum. And the scalar multiplication, of U and C is given by the following. It's C, the scalar, right, times the U vector, which will be nothing else than just C times U1, C times U2, and all the way C times UN. So that's how we're going to define the scalar multiplication. Well, as you can imagine, as in as in R2 or in the 2 space, we can define the negative vector, and therefore we can define the subtraction. So the subtraction of two vectors of U and V, as you can imagine, this is nothing else. So it's U vector minus V vector is U1 minus V1, U2 minus V2, and we go all the way to UN minus Vn. So this is how we're going to subtract two vectors. We said many times, the subtraction of two vectors is like addition. The only difference is that when you add the first vector with the opposite of the second vector, which is basically negative V. So that's what you do. There's nothing. So this guy here, let me say it again, is U plus negative V. That's it. But you can also write it component-wise. And now the zero vector, let me say it as a remark here. So the zero vector which is this, has components, as you can imagine, 0, 0, 0. And you can add it with any vector. You can multiply by any scalar and so on. Okay, so these are the operations. Now, let me give you a quick example of vector operations in R3, let's say. So an example, vector operations in R3. let's say, let me consider this. You can take vectors in R4, R5, whatever, but it's more convenient to take in R3. So let's take these vectors of component -1, 0, 1, and V of components 2, -1, 5 in R3, right? So we want to compute the following. We want to compute -2 times U vector plus V vector. So compute. So we want to compute these. Well, as we have seen previously, this is nothing else than just the basic operations that we have done for vectors in the plane. So we're going to do the same thing here. So this is nothing else than just multiplying the scalar -2 times U vector plus the V vector. Okay, let's do it. So this is -2 times, I'm going to write the vector U -1, 0, 1 plus the vector V, which has the components 2, -1, and 5. So this will be 2, 0, -2 plus 2, -1, and 5. As somebody says here, as Neil says, is 4, -1, and 3, correct. Yeah, that's the vector. So the same operations you can perform in R4, R5, and so on. Okay, I'm not going to dwell too much on these examples. Well, if I look back at all these properties for vectors in Rn, so let's call this properties of vectors in R2. So guess what? The same theorem will hold true for vectors in Rn. So because I don't want to write it again, this is very important. The same properties for R2 are valid for vectors in Rn. The same. So you can add them. The addition is closed. You can subtract them. It's the same thing. You can you have the associativity property, so it doesn't matter which way you add them. You can also you have associativity. You can add the by the null vector in Rn. We'll give it the vector. You can define the opposite vector, so you can define negative U and so on. And the same thing happens for the scalars. We have scalar multiplication, you have this distributivity property, multiplicative identity, and so on. So the same properties will hold true. So when I say this, I mean from this theorem, this long one, because I don't want to write it again. So properties of vectors in Rn, the same thing will happen for properties of vectors in from R2. The same thing will happen for the same properties will hold true for vectors in Rn. Imagine this theorem is the same for Rn. Okay. Now, the same thing you can do with the vectors operations in R4. I don't want to do it. I'm just going to give you this example for you as an exercise. It's example 5 from the notes. And this will be page, if you want, page 118. Says the following. So we define two vectors in R4. So this will be 2, -1, 5, and 0. V will be 4, 3, 1, and -1. And W, I define another vector, will be -6, 2, 0, and 3. So these are vectors in R4. And the same type of operations we can. So we are asked to, okay, in fact, let's do one of them. Find X. We need to find this X using, in fact, let's do it. Using each equation. A, X equals 2u minus v plus 3w. B, 3x plus w equals 2u minus v plus x. So we need to find this x, who this x is. What do you think? Is x a vector? Is x a scalar? I didn't put anything there. So what do you think? Okay, somebody, Neil says vector. What else? Does anybody have any other opinion? You have only two options though, either a scalar or a vector. Well, somebody, it looks like everybody agrees with the vector, so okay. Yes, it's a vector. It's quite clear. Since u and v and w are vectors, so definitely, and you have an equation in terms of the vectors, there is no way for that x to be a scalar, for example. It has to be a vector, right? Okay. Okay, so let's do this. Let's take x from the first one. So x will be what? So x will be, I can write it. So it's 2 times the vector u is 2, -1, 5, and 0, minus, and let's be careful here, the vector v, which is 4, 3, 1, -1, plus 3 times w, which is -6, 2, 0, 3. Okay? So this will be equal, if we do all these computations, keep in mind that we have a scalar here, 2 is a scalar. So we will have what? We'll have 4, -2, 10, and 0. And here minus, let's do the, it's 4, 3, 1, -1, plus, and here I have -18, 6, 0, 9. Okay, and once we do all these computations, we will have the following. So it will be 4, -2, 0, 10, 0, minus, and here I have, this will be -14. In fact, I don't need to write it like this. So it will be -14. 9, 1, and 8. Okay, and once you do these computations, you have that this will give you, pay attention, we have a negative in front of it, so this will give you 18, -11, 9, and -8. Okay, so this is how we found the x. Now for part B, it's the same thing. I'm not gonna do it. I'm just gonna tell you the idea. So you just isolate x in this equation. So this will be that x will be equal to, oh, we also have a 3 times x. Okay, let's do the computations a bit. So we have 3 times x plus 3 times w equals 2u vector minus v vector plus x. Okay, we're gonna, and this will be equivalent with 2x equals 2u vector minus v vector minus 3w vector. And now guess what? I will divide by the scalar 2. So this will be 1/2, let me put it like this, times 2u vector minus v vector minus 3w vector. Or if you want to do the operations, it will be u vector minus 1/2 times v vector minus 3/2 times w vector. And now you have the scalars and you do the operations. Okay, I'm going to leave it to you. So etc. So this is an exercise for you to finish it off. Anyway, you can find it in the notes as well. Too much? I don't understand. Too much computations? Well,
Yeah, too much work.
too much work. Ah, okay, I see. Anyway, you never know. All right, so now now I want to veer towards some properties of the additive identity and additive inverse. So this will be very important. So theorem. I don't know, for the way I'm moving right now, I think I'm going to need 3 lectures for vector spaces. Probably I'm going to do an extra one. Right now I'm not in Texas, so for me now it's almost 1 p.m. So it's but next week on the Wednesday I'll be back in Texas. So probably I'm going to do another extra lecture for vector spaces because I don't want to rush through things too much. I want everything to be like all the details to be there, at least most of them. Well, this theorem, like I said, it concerns the properties of additive identity and additive inverse. Okay, so let's see. Let say V be a vector in Rn, and let's C be a scalar. Okay, so we have a vector and we also have a scalar. And now we want to see what kind of properties we have. So the following properties below are true. A, let me write it in words, the additive identity is unique. This is very important. That is, let me explain what this means. That is, if v vector plus u vector equals v vector, then the u vector must be the null vector, right? B, the additive inverse is also unique. The additive inverse of V, and we have seen what that means, is unique. That is, if V vector plus U vector equals 0 vector, then U vector is equal to negative V. That's what it means. And of course, as you can imagine, when I multiply, let's see, when I multiply the vector, the scalar 0 by the vector V, pay attention, this is the scalar, this is a vector. That's why I like to distinguish them by putting some arrows. Like I said, if you feel if those arrows above the vectors disturb you, then okay, don't put them. But I want to make myself clear so that you're not gonna mess these two. So when I put the arrow above something, I'll consider that a vector. When I don't have any arrow there, then that is a scalar. So now I have the multiplication between the scalar 0 and the vector v. What do you think we're going to obtain here? What do you think? What is the result? Okay, 0, but 0 what? Is the 0 scalar or the 0 vector? The 0 vector, correct. So I'm going to put it like this, right? All right, great. So another property, let's say if we have something like c times 0 vector, it will give us what? So I have a scalar now by a real scalar, and I'm multiplying by the null vector. What are we going to get? We're gonna get the 0 vector, right? So we're getting the 0 vector. Okay, and now another property is the following. If we have c times v, pay attention, is the 0 vector, then guess what will happen? Either the scalar is 0 or the vector v is 0 vector. And also another property that we have is that the negative v is the same as the vector v. Okay, so these are the main properties of the vectors. I want you to pay attention. In my notes, unfortunately, you might get confused because I didn't put the arrow. So it's kind of like I should have put a bold, right? So that I can symbolize that that bold character is of a vector, and that's not bold, it's a scalar. But in this video, so probably this video will make things clearer for you. And now, do you have any questions so far regarding this? Okay, so probably I assume that everything is it's pretty easy up to this point. Okay, that's great. And now I want to talk about linear combinations of vectors. This is very important. Linear combinations of vectors. So so an important type of a problem in linear algebra involves writing the vector x as the sum of scalar multiples of each other vectors. Let's say v1, v2, vn. So this means that we can write the vector x as, let's say, c1 times v1 plus c2 times v2 plus all the way to cn times vn. So this is what I call a linear combination. So this is what we call, this is a linear combination. You see, you write the vector x as a linear combination so of vectors v1, vn. In other words, you write it as a sum of scalar multiples of each vector by each vector v1, vn by c1, cn. So that's the linear combination of vectors v1, V2, Vn. That's what it means. Okay. Now let's see some examples. We want to see what kind of vectors we can write as a linear combination of other vectors. Let's give a quick example. So example. And let's consider the following vector. So we want to write a vector as a linear combination of other vectors. So well, let's consider x to be, let's say, -1, -2, 2. So I'm going to consider vectors in R3. 0, u is 0, 1, and 4, and v is -1, 1, and 2. And let's consider another one, and w is 3, 2, 3, 1, 2 in R3. So I want to make myself clear that these vectors are in R3. And now we're asked to the following. Pay attention, which will go back to this writing here. We're asked the following. Find the scalars. So find scalars A, B, and C such that this x vector is A times u plus B times v plus C times v. In other words, I could have said plus C times w. In other words, I could have said that find, or I could have just said it directly, write the vector x as a linear combination of vectors u, v, and w. In other words, the translation of that will be just the statement that you see here, to find the scalars a, b, and c such that that vector x is a times u vector plus b times v vector plus c times w vector. So that's the linear combination. Okay, so let's do this. So in other words, we just have to do the basic operations with vectors. So let's do it. So we have this vector x, which is -1, -2, and 2. So this is my vector, let's say x. And this is written as a times the vector u, which has components 0, 1, 4. So this is my u here. Plus b times -1, 1, 2. This is my v. Plus c times my vector w, which has components 3, 1, and 2. And this is my w. All right, once we do all these computations here, so let's do it. We're gonna get the following. So, okay, let's write it. 0a for a plus -b, b, 2b plus 3c, c, and 2c. Okay, and once we add up these three vectors, we will get -b plus 3c, a plus b plus c, and the last component will be 4a plus 2b plus 2c. And we know that this vector, let's keep in mind that this vector is -1, -2, and 2, right? Let's keep this in mind. So from here, the first thing that we learned in this class was the equality of vectors. This will be nothing else than just we obtain the following system. So equating the corresponding components, we'll have the following system. So the system is the following. Negative, let me write like this, b plus 3c is -1. A plus b plus c is -2. And 4a plus 2b plus 2c is 2. What did we obtain? Can you tell me what this is? A matrix? Not quite. Look at it. It's a system of linear equations, right? So this is system of linear equations. Right? It's a linear system. We have 3 equations, 3 variables, right? And you see how I go back to what we learned in the first chapter? So systems of linear equations, you have plenty of ways of solving systems of linear equations. You can use just the substitution method directly. You can use elimination method, or you can use the augmented matrix and perform elementary operations on that matrix. So what we call the Gaussian elimination, or maybe you can go even further using Gauss-Jordan elimination. Then you can also have other options as well, like in the review session, I've done this Cramer's rule, which will involve the determinant of a matrix. You have plenty of options of solving the system of linear equations. So I'm going to leave it to you as an exercise to solve it. It's a good practice for the midterm exam and even for the final exam, so that you know how to solve this. But anyway, it's very easy. I don't want to lose my time with solving this, but I'm just going to tell you directly. Once we solve this once we solve this for A, B, and C, we get the following set of solutions. A, B, C, as you can imagine, has a unique solution. Will be 1, -2, and -1. So that's the solution for the system. And now, once I found A, B, and C, then I can definitely write my vector X as a linear combination of U, V, and W, which is 1 times U vector plus -2 times V vector plus -1 times W vector. So this is the linear combination of X. The vector X is a linear combination, so the vector X is a linear combination of vectors U, V, and W. So that's what it means for a vector to be a linear combination of other vectors. Of course, sometimes I'm going to point out the remark. I hope this is clear for you how to represent vectors as a linear combination. You will see that this notion will be very important as we go further on into the material. You will see once we study about the spanning sets and so on. You will see that these will, once we learn more stuff about subspaces. Anyway, you will see. And now I want to point out a remark. And I think with this, I'll be done for today. Probably I will need 3 lectures. So, okay, the remark is the following. So sometimes it's useful to represent a vector. Let's say if I have a vector U of U1, U2, UN. So this is in Rn. So sometimes it's good to represent it either as a, can be represented either as 1 by n, let's say row matrix. So you can write it in this way, just like we have, or you can say row vector to be more row vector. Or an n by 1 column, or to be more specific, column vector. Well, for example, you can write it like this. So just like the way we have write it here, right? As a row matrix or row vector, or you can write it like this. Let's say U is, you can write it as a column. U1, U2, UN. And of course, if you want to represent another vector, let's say V1, V as V1, V2, Vn, you can add them easily, just the way you have seen. U plus V vector, it will be, so let's write them as column vectors. And guess what? The same thing will happen as you might expect. This column vector will have the components U1 plus V1, U2 plus V2, and we go all the way to UN plus Vn. And that's it. And the same results for the operations would hold true even in this case. So it doesn't matter how you write them. You can write them as a column vector. You can write them as a row vector. It doesn't really matter. Okay, guys, I think I'm going to stop here today. Next time I will talk. I'm at this point, I'm pretty sure that I will need an extra lecture. So we said we will spend 2 weeks on this, but we will probably need another extra lecture. Probably I'm going to do it sometime next week on Thursday. I don't know exactly when, but probably that's going to be the case. Anyway, we'll see. Thank you very much, and I'll see you. We'll see each other next week. But now I want to say a few words about the exam before I take the attendance. So the exam we said is going to be on July 2nd, right? It will be a 24 hours exam. You'll get the instructions probably tonight. I will send you the instructions, or tomorrow. Also, I'll post the exam. I'll upload it on my website. You'll get the instructions and the precise instructions via email and also Blackboard. Okay, let me stop the recording and then I'll take the attendance.